The information contained in this presentation is intended for general informational purposes only. The presentation is not a substitute for a review of the applicable government regulations, codes, OSHA standards, or other regulations, and should not be construed as legal advice or opinion. Specific questions should be referred to the proper regulatory authorities, electrical engineer, licensed electrician, or attorney. To help understand voltage, imagine a water tank at a certain height above the ground. At the bottom of this tank, there is a pipe. In this analogy, the pressure at the end of the pipe represents voltage, and the water in the tank represents charge. The more water in the tank, the higher the charge will be, and the pressure will be higher at the end of the pipe. To help understand amperage, you can think of the amount of water flowing through the pipe from the tank as current. The higher the pressure, the higher the flow, and vice versa. Let's say now that we have two tanks, each with a pipe coming from the bottom. Each tank has the exact same amount of water, but the pipe on one tank is smaller than the pipe on the other. We would measure the same amount of pressure at the end of either pipe, but when the water begins to flow, the flow rate of the water in the tank with the smaller pipe will be less than the flow rate of the water in the tank with the bigger pipe. In electrical terms, the current through the smaller pipe is less than the current through the bigger pipe. In order for the flow to be the same through both pipes, we would have to increase the amount of water, or charge in electrical terms, in the tank with the smaller pipe. This increases the pressure or voltage in electrical terms at the end of the smaller pipe, allowing more water through it. This analogy demonstrates how an increase in voltage causes an increase in current. To help explain ohms or resistance, consider again our two water tanks, the one with the smaller pipe and the other with the bigger pipe. It stands to reason that we can't fit as much volume through a smaller pipe than a bigger one at the same pressure. This represents resistance. The smaller pipe resists the flow of water through it, even though the water is at the same pressure as the tank with the bigger pipe. Resistance is measured in ohms. Taking the analogy one step further, I'll add in automotive terms to help explain the concept. Let's look at these terms individually. Voltage is the potential to develop a current across a conductor. The higher the voltage or potential, the higher the possible current that will pass through a conductor at a certain resistance. Voltage is also analogous to pressure in hydraulics. Higher pressure means a higher potential to get more water through a certain size pipe. Engine power is rated in a unit called horsepower. The power of a car's engine won't indicate how high a hill it can climb or how much weight it can tow, but it will indicate how fast it can climb a specific hill or tow a specific weight. Volts are analogous to pressure in the water pipe. It's the push that the tank exerts on the pipeline downstream from the tank. Let's say you increase the diameter of the pipe from the tank. You probably guessed that this also makes more water come out of the pipe. This is like decreasing the resistance in an electrical system, which increases the current flow. In vehicle terms, torque is the amount of twisting force produced by the engine. The power of an engine is a function of both the RPMs and its torque. Neither speed nor torque alone is a measure of an engine's power. If all of the faucets in your house are closed, no water will flow through the pipes. If you open one faucet, some water flows. If you open all of the faucets, a lot more water flows. This flow of water is similar to electrical current. Current is the flow rate of electrons through the circuit. Take a hose and point it at a water wheel, like the one that were used to turn grinding stones in water mills. You can increase the power generated by the water wheel in one of two ways. If you increase the pressure of the water coming out of the hose, it hits the water wheel with a lot more force and the wheel turns faster, generating more power. If you increase the flow rate, The water wheel turns faster because of the weight of the extra water hitting it. With an engine, if you increase either RPMs or torque, you will increase horsepower. Resistance is like the orifice size of a power washer spray nozzle, with a smaller orifice causing higher resistance and requiring higher pressure or voltage to push a certain amount of gallons per minute or current through. This is why you experience reduced water pressure with plugged pipes, and how friction in an engine increases resistance, thereby reducing its horsepower. Current, not voltage, does the work in electrical circuits. The flow of water through a turbine is what makes the turbine spin. The flow of current through an electrical circuit is what lights the bulb, heats the stove, runs the motor, etc. Routing and controlling the flow of current is the goal of every electrical circuit. To demonstrate this, a water pump creates pressure, or in electrical terms, voltage. The pipe size determines the resistance, representing ohms in electrical terms, which produces the gallons per minute flow rate, or current in electrical terms. Here's another way to look at it. Both of these vehicles have the potential to go 55 miles per hour. Wouldn't you agree? Now let's add a load into the equation. Assuming both of these vehicles could carry the weight, which the one can't, but for the sake of discussion, let's assume that they can. Which of these two vehicles would you choose to get the job done? Okay, I'm hoping you guessed correctly. I can tell you which one I chose. If you picked the other vehicle, I would suggest you go back and review this chapter again. Voltage oftentimes gets the most attention, but let's take a look at the difference between a little 9-volt battery and a huge 6-volt golf cart battery. The 9-volt battery may have a higher potential, but when it comes right down to it, the golf cart battery will be able to deliver 200 amps, way more than the 9-volt battery. Amperage in a small battery like a 9-volt is measured in milliamps, represented as mAh. This means the battery could power a half-amp load for 1 hour. Data I have seen shows the best alkaline 9 volts being between 0.3 and 0.5 amp hours, or 300 to 500 milliamps, while a golf cart battery can store 180 to 225 ampere hours, represented as AH, which means it could power a half-amp load for 360 to 450 hours. Sometimes a little education can make one more careless than before, as someone feels more comfortable in their knowledge. There is a cardinal firearm safety rule that says, treat every firearm as if it is loaded. That can be applied to working with electricity. Treat all electrical as if it is energized. By making this assumption, you will reduce your chances of an unwelcome surprise. If you make a mistake in plumbing, you might make someone unhappy. Make a mistake in air conditioning, and someone might be uncomfortable. But a mistake with electricity, and you could injure or kill yourself or others. I realize that probably most of you watching this have already been shocked by electricity and obviously have lived to tell about it. Unfortunately, the more that occurs, the more it tends to lower our defenses. Please never take safety for granted, and always treat electricity with the respect it deserves. Your life and the life of others may depend on it.